Good evening, my friend. The day has done its work, and now the quiet has come to take its gentle place. Let the noise of the world fade to the edges while you settle into stillness. Find a spot where your body can rest and your mind can loosen its hold. Feel the rise and fall of your breath like soft tides against a distant shore. Each inhale brings calm. Each exhale lets go of what's left behind. You're safe here, surrounded by quiet, ready to drift wherever the stars may lead. Tonight, we'll drift together through a quiet question, one that has followed humanity for as long as we've looked at the stars. Is there still something left to discover out there? And if there is, what secrets might be waiting in the dark between galaxies? There's no rush to find the answer. We'll move gently, letting curiosity guide us like a faint compass light. Perhaps we'll uncover a few wonders, or simply rest in the beauty of not knowing. If these soft explorations bring you peace, you can like and subscribe. It helps this small corner of calm reach others who need it too. Now, let's begin our quiet journey. Somewhere in the deep stillness of space, far beyond the wind and the tides, a star is born. It begins not as light, but as a whisper in darkness, a slow gathering of dust and gas, drifting together for ages inside a cold cloud called a nebula. Gravity, patient and invisible, pulls at this cloud, folding it inward until its heart grows dense and warm. The pressure builds quietly, then fiercely, until atoms begin to fuse and a spark of creation ignites. And so, a star opens its eyes for the first time, glowing with the breath of a new universe. A star is not made of fire, but of plasma matter so hot that it dances as light. It holds itself together through its own gravity, balancing the pull inward and the push outward in a delicate harmony that can last billions of years. Our own sun, the nearest star, burns in that same balance. Its warmth cradles Earth, giving rise to oceans, forests, laughter, and sleep. Every sunrise you have ever seen is the steady heartbeat of that star, still pulsing after 4.6 billion years. At night, when the world grows quiet and the air cools against your skin, other stars reveal themselves countless tiny points, each one a sun in its own right. They appear fragile, flickering, but only because they are impossibly far away. Light from the nearest ones has traveled for years to reach us. Others began their journey long before any human walked the earth. The universe holds somewhere between 10 sextillion and 1 septillion stars, numbers too vast to imagine. Yet only a few thousand can be seen by the naked eye, all of them dwelling within our Milky Way, a soft spiral of stars drifting like a silver mist across the sky. Long before telescopes, people looked up and tried to make sense of those lights. They connected the brightest ones into shapes: hunters, bears, rivers, queens. Constellations became maps of stories, patterns that helped ancient travelers find their way home. Farmers read the heavens to mark the seasons, and priests traced the sun's path to build calendars. The stars became both compass and myth, guiding ships across dark seas and marking the rhythm of time itself. The heavens, they believed, were perfect and eternal, a dome of light that never changed. But the sky, like all things, was alive. In the quiet centuries that followed, the heavens began to reveal their secrets. In Egypt, more than 3,000 years ago, careful eyes mapped the stars upon parchment. In Babylon, astronomers kept their first catalogs, clay tablets etched with names and numbers, preserving the positions of constellations across seasons. In Greece, thinkers like Aristoteles and Timocharis charted the motions of the brightest lights, while Hipparchus, in a moment of awe, recorded the sudden birth of a new star, the first nova ever written down. The Chinese skywatchers, too, noticed what others had missed. The heavens could change. They saw brilliant stars appear and fade supernovae that blazed for weeks, brighter than any planet, before vanishing into silence. One of them, the great flare of the year 1006, lit up the night so fiercely that people could read by its glow. Another, in 1054, left behind the swirling ghost we now call the Crab Nebula, the remains of a star's final breath still drifting through space. In time, the gaze of wonder passed from one culture to another. Arabic astronomers gave the stars their lyrical names: Aldebaran, Betelgeuse, Rigel, Vega, words that sound like music when whispered into the night. They built great observatories under the desert sky, charting not just single stars, but clusters and nebulae. In the 10th century, Al-Sufi described the soft smudge of light we now know as Andromeda, the nearest spiral galaxy to our own. Others, like Al-Biruni, dreamed that the Milky Way was not a mist at all, but a river of countless stars, seen from afar, a thought both daring and true. As centuries passed, new eyes looked upward. In Europe, Tycho Brahe saw new stars appear, proof that the heavens were not unchanging. Giordano Bruno imagined that every point of light was another sun, each with its own worlds, perhaps even other Earths, where someone else might be wondering the same thing. William Herschel, scanning the sky with a telescope of his own making, counted thousands of stars and discovered that they were thickest toward a shining band, the heart of our galaxy. His son, John Herschel, continued the work in the southern hemisphere, revealing that the sky below was no less full than the one above. When light was broken into color, another truth emerged. Early in the 19th century, Joseph von Fraunhofer noticed dark threads crossing the rainbow of starlight absorption lines, each one a fingerprint of the elements within. Angelo Secchi, studying these patterns, began to group stars by their spectra, creating the first map of stellar families. Some stars, he found, were cool and red, others blazed white or blue. Annie Jump Cannon would later refine this system, giving each star a place in a great alphabet of light, a quiet order to the cosmic choir. A star's story, though, is written not just in its color, but in its distance and motion. Friedrich Bessel, in 1838, measured the tiny wobble of a star named 61 Cygni as Earth moved around the Sunday. From that gentle sway, he learned the star was over 11 light-years away, the first true measure of stellar distance. It was as if the universe had stretched open, revealing that even the nearest suns lie across an ocean of space. Not all stars live alone. Some move in pairs, circling one another in slow, eternal dances. The brightest star in our sky, Sirius, hides a faint companion that tugs gently on its light, a white dwarf, small and dense as memory. In 1899, Edward Pickering noticed something extraordinary. The light from a star called Mizar seemed to split and rejoin, again and again. It was the first spectroscopic binary, two stars orbiting so closely that only their shared heartbeat could betray their presence. Astronomers like Struve and Burnham would spend years tracing such motions, learning to weigh stars by the grace of their orbit. Then came the age of photography. The cold glass eye of the camera saw what the human eye could not. Carl Schwarzschild found that a star's color could reveal its temperature: red stars cool and patient, blue stars fierce and young. With new instruments, astronomers measured brightness with exquisite care, turning night into data, light into language. In 1921, Albert Michelson used an interferometer to measure the size of a distant star, not its light alone, but its very breadth across space. The universe, once unreachable, had begun to yield its scale. By the early 20th century, starlight had become the alphabet of the cosmos. The Hertzsprung-Russell diagram, born from this light, showed how stars evolve where they are born, how they shine, and when they fade. On that quiet chart lies every fate: small stars that burn slowly and endure, giants that blaze briefly and die young. It was no longer myth, but a living story, written in energy and time. And then came a revelation so simple, yet so profound it changed everything. Cecilia Payne-Gaposchkin looked into the starlight and saw not iron or stone, as others believed, but hydrogen and helium, the simplest elements, the building blocks of everything. Stars, she realized, were made of almost nothing, and from that nothing came all things. Through fusion in their hearts and explosions in their deaths, they forged the heavier elements: carbon, oxygen, gold, the dust that would become our bones, our oceans, our hearts. So when you look up at the night sky, what you're really seeing is memory light that has traveled across time, telling the story of creation in every flicker. The atoms in your blood were once part of a star's burning core. You are, in the most literal sense, starlight that learned to rest and dream. Let that thought settle with you now, quiet, infinite, and kind. The stars are not distant strangers. They are your ancient kin, whispering across the dark. And as you drift into sleep, the same light that shaped the universe keeps its gentle vigil above, waiting for you to dream among them once more. Most of what we truly know about the stars comes from the quiet neighborhood we inhabit, a small gathering of galaxies called the local group. Here, inside this cosmic village, the Milky Way drifts among its companions: the Andromeda Galaxy, the Triangulum, and dozens of smaller ones, each carrying its own clusters of ancient suns. Within this familiar space, astronomers have traced the stars with patience and care, mapping their colors, temperatures, and motions across the spiral arms of our home. Each point of light becomes a word in the language of the cosmos, written on the dark page of the sky. And yet, even beyond the soft disk of our galaxy, a few lights whisper from astonishing distances. Some are variable stars like the Cepheids, whose brightness pulses in perfect rhythm, their steady beat allowing astronomers to measure the vastness between galaxies. In the Virgo cluster, stars have been found within M87 and M100, tiny flickers that bridge the darkness between worlds. But sometimes, the universe offers a deeper kind of miracle. When the light from a distant star passes through the gravity of another galaxy, it bends, like starlight through a curved glass. Einstein once predicted this bending gravitational lensing, a cosmic magnifying glass that can reveal what would otherwise be invisible. Through this strange trick of space and time, astronomers once glimpsed a single star called Icarus, its light traveling nearly 9 billion years before it reached us. A single heartbeat from the dawn of the universe, magnified by the gravity of all that lies between. Long before we understood these celestial wonders, people looked up and began to weave the stars into stories. On clear nights thousands of years ago, when there were no cities to wash away the dark, the sky must have felt close enough to touch. In ancient Babylon, stargazers saw patterns among the scattered lights and gave them meaning: the shape of a bull, a scorpion, a river of stars. These constellations became a mirror of human thought, turning the silent heavens into a tapestry of gods, heroes, and creatures that told of creation, love, and loss. Along the path, the sun seemed to wander each year. They noticed 12 special constellations. That path was the ecliptic, the invisible highway the sun travels through the sky. Those 12 constellations became the foundation of astrology, a way of tying human lives to the motions of the stars, of finding order in the slow turning of the heavens. And though science later moved beyond those beliefs, something tender still lingers in the idea that the stars and our stories are somehow woven from the same thread. Many of the stars shining in those constellations were given names that have survived across centuries. Arabic, Latin, Greek, the sounds of old languages still echo when we speak them. Betelgeuse, Altair, Antares, Deneb. To name a star was to remember it, to pull it a little closer from the infinite. For astronomers, naming was not only a method of cataloging, but a quiet act of storytelling. Each bright point became a character in the sky, a note in the great human song of wonder. To the Greeks, not every shining point was a star. A few seemed restless, wandering across the night from week to week. They called them planetes, wanderers, and linked them to gods. Mercury, the swift messenger; Venus, the radiant goddess of love; Mars, the red god of war; Jupiter, the great protector; and Saturn, the slow keeper of time. Far beyond the reach of their eyes, other wanderers waited: Uranus and Neptune, unseen in the ancient dark, their faint light too delicate to pierce the human gaze until centuries later. As knowledge deepened, patterns gave way to precision. In the early 1600s, the German astronomer Johann Bayer drew careful star maps, assigning Greek letters to each star within its constellation. Later, John Flamsteed organized the heavens with even greater order, numbering stars by their position in the sky, a celestial longitude called right ascension. His Historia Coelestis Britannica, published in 1712, became the quiet backbone of modern star charts. These systems remain today, a bridge between ancient imagination and modern science myth, reshaped into measurement. Now, the guardianship of names rests with the International Astronomical Union, the IAU, a council of astronomers who keep the sky in careful balance between tradition and truth. Their working group on star names ensures that each star's name, whether ancient or newly chosen, belongs properly in the shared story of discovery. Even so, there are those who try to sell names for stars, certificates printed with promises of ownership. But stars cannot be bought. They belong to no one and to everyone. The sky resists such claims, just as the ocean resists being held in a single hand. To describe a star, astronomers often turn to our sun as the measure of all things. Its light and weight form a cosmic standard, a single flame by which all others are compared. A star might be 2 times brighter than the sun, or half as massive. Its warmth might be measured in solar temperatures, its gravity in solar pull. In 2015, the IAU fixed these solar values, giving the universe a common rhythm to count by. The sun's mass, they declared, would stand at 1.9885 times 10 to the power of 30 kilograms, a number vast enough to quiet any thought of comparison. And when distance grows too large for language, astronomers use the astronomical unit, or AU, the span between Earth and the Sunday. 93 million miles of space, a distance so ordinary to our orbit, and yet so breathtakingly immense. In 2012, this number, too, was made exact: 149,597,870,700 meters, a precise breath in the scale of infinity. Yet, even in this grandeur, the birth of a star begins in stillness. Deep in clouds of gas and dust, molecular clouds, the seeds of stars rest in darkness, colder than ice. These clouds are so thin that they make the emptiest vacuum on Earth seem crowded, and yet they hold enough material to build thousands of suns. Within them, gravity begins its quiet work, drawing particles together grain by grain until, deep inside, a glow stirs. The Orion Nebula is one such place, a cradle of stars glowing softly against the night like the ember of a cosmic fire. Within those nurseries, stars are born in clusters, from a few dozen to hundreds of thousands, each one carrying the potential for worlds and light. The most massive among them shine fiercely, pouring out radiation that carves the clouds around them into glowing regions known as high second, vast spheres of ionized hydrogen. Their brilliance is both creative and destructive. The same energy that illuminates also tears the cradle apart, scattering the dust and halting new births. Creation and destruction, forever entwined in the rhythm of starlight. Every star, once formed, settles into its long middle age, what astronomers call the main sequence. Here, it lives in balance, fusing hydrogen into helium in its core, shining steadily for eons. But no two stars follow the same story. Their lives depend on their mass, their inner weight decides their destiny. The smallest ones, less than half the mass of our sun, live the longest. They stir themselves from center to edge, evenly blending their fuel. They will never swell into giants, never cast off their outer shells. Instead, when their hydrogen is finally gone, they will fade into quiet white dwarfs made of helium, small, steady embers that may outlive the universe itself. Stars like our sun live more dramatic lives. When their hydrogen runs out, they expand into red giants, their surfaces cooling and glowing with soft crimson light. They begin to fuse helium into carbon, then shed their outer layers into space, creating vast, delicate shells of gas, planetary nebulae that drift like stained glass through the night. What remains behind is a white dwarf, the still, dense heart of what once was a sun, glowing faintly with the memory of all it has given. Heavier stars, those 2 to 8 times the sun's mass, follow a slower path, their cores burning quietly through stages of fusion. They spend long years in a stable glow called the red clump phase, before ending their lives as white dwarfs as well. Their beauty lies not in the violence of their end, but in their endurance, their patient shining through cosmic time. And somewhere among them, in the deep fabric of space, new stars are already forming, their light not yet born, but promised. The universe, vast and restless, keeps breathing, stars dying, stars awakening, each one a fleeting flame in an endless night. In the far silence of space, where gas drifts like pale smoke and cold dust gathers in endless spirals, some stars are born too heavy to last. With more than 8 times the sun's mass, they blaze through their lives like brief, bright songs. They burn hydrogen quickly, grow into swollen supergiants, and fuse heavier elements in their hearts until the balance breaks. Then, in a single breath, their cores collapse and they explode as supernovae, scattering gold, iron, and oxygen into the dark. Out of their death comes life again. The dust of such giants becomes the clay of planets, the breath of oceans, and, one day, the matter that dreams. But before that final flare, every star begins in shadow. Deep inside immense molecular clouds, cold and slow as fog, gravity starts its quiet work. A tiny region grows denser than the rest. A shock wave passes through, maybe from a nearby star's explosion or from galaxies brushing past each other. Balance falters, and collapse begins. Astronomers call this the gene's instability, the moment when gravity wins and the fall cannot be stopped. As the cloud caves inward, it fragments into smaller, darker knots, known as Bach globules. Inside each, matter folds toward its own center, heating as it compresses. When the tug inward and the pressure outward finally find equilibrium, a small object flickers into being a protostar, the embryo of a sun. Around it, a disk of gas and dust spins like a slow whirlpool. From that disk, planets and moons will someday form. The young star glows not from fusion yet, but from the warmth of its own collapse, gravity turning itself into light. This tender stage lasts millions of years. A star like the Sun may take 10 million to grow steady, while a tiny red dwarf might spend 100 million years finding balance. These newborn stars have names like Lullabies, T, Tauri, and Herbig, depending on their size. They shoot narrow jets of gas from their poles, elegant streams that carve the surrounding cloud into glowing patterns called Herbig-Haro objects. The jets spin away excess energy, helping the star calm its rotation, while its light clears the cradle of dust that once held it. Smaller T Tauri stars follow a slow, cooling path called the Hayashi track. They shrink while keeping nearly the same temperature, dimming gently until hydrogen fusion begins. More massive ones trace the Henye track, growing hotter and brighter as they mature. When that first spark of fusion ignites, the star steps onto the main sequence, a long and steady rhythm that can last for billions of years. Most stars are not solitary. The clouds that bear them often split, dividing angular momentum into pairs or trios. Two stars born together form a binary system, orbiting one another in a silent dance. Some stay loosely bound and drift apart. Others cling close, their gravities intertwined for life. Over time, their fates merge, one feeding the other, or both aging together until their light fades. Once settled, a star spends 90% of its life in quiet labor. Deep inside, hydrogen turns into helium through fusion, a process of unimaginable heat and pressure. From that core, energy travels outward, spreading across layers until it escapes as light. The Sun, during its billions of years, has grown about 40% brighter since its youth, a gradual rising of flame. Every second, it loses a whisper of itself in solar wind, a stream of charged particles blown into space. For small stars, this loss is negligible. For giants, it is extravagant. Some shed a millionth of their mass each year. The biggest may lose half their body before their youth ends. Lifespan depends on size. The Sun will shine for about 10 billion years. The largest stars burn through their fuel in only a few million. But the smallest red dwarfs, less than a quarter of the Sun's mass, sip their hydrogen so slowly that they could live for 1 trillion years, far longer than the universe has yet existed. None of them have died. They are still young in a cosmos that is only 13.8 billion years old. A star's makeup also shapes its story. Astronomers call everything heavier than helium metals. The fraction of these elements, a star's metallicity, affects how it burns, how strong its magnetic fields are, how fast it sheds its mass. The earliest stars, formed when the universe was young, contained almost no metals. They were simple, pure hydrogen and helium. But each generation of stars enriched space with heavier elements, so the next would be born more complex, with the raw materials for planets and life. In that way, the universe learns and remembers. When a star about half as massive as the Sun or larger exhausts its core hydrogen, the quiet balance ends. Fusion shifts to a shell around a helium core, and the outer layers expand. The surface cools, turning red, and the star swells into a giant. Its gravity loosens, allowing winds to carry matter away, dust rich in carbon, nitrogen, and oxygen. In time, that dust will seed new clouds, ensuring the cycle continues. Our own sun will follow this path in about 5 billion years. It will grow so large that its edge may brush the orbit of Earth, glowing 250 times wider than today. When the helium core grows dense enough, it becomes degenerate, so tightly packed that atoms cannot move freely. Heat rises until helium ignites, all at once, in what astronomers call a helium flash. For a brief moment, fusion runs wild inside, forcing the star to contract and stabilize. Its outer layers shrink, and it enters a calmer phase on the horizontal branch, burning helium quietly into carbon and oxygen. More massive stars skip the flash and slide into this new balance smoothly. Many spend millions of years glowing softly in what's known as the red clump. When helium finally runs out, fusion moves outward again, forming shells of burning hydrogen and helium around a carbon-oxygen core. The star swells into what's called the asymptotic giant branch, or AGB. It looks much like a red giant, but brighter, pulsing with unstable rhythms. With each pulse, the star shakes off more of its envelope, sending waves of enriched gas into space. Convection stirs its insides, bringing fresh carbon to the surface, and over time, it may lose more than half its mass. What remains is small, but fierce, glowing at the center of an expanding shell of gas, a planetary nebula. These nebulae float through space like delicate lanterns, fading slowly as the white dwarf at their core cools over billions of years. The more massive the star, the more violent its finale. Those starting with 9 or more suns live fast and die in grandeur. After leaving the main sequence, they expand into brilliant blue supergiants, then into red ones, fusing heavier and heavier elements, carbon, oxygen, silicon, until the core becomes iron. But iron cannot give back energy through fusion. It is the dead end of creation. When the core grows too heavy, it collapses in an instant, and the star explodes as a supernova, bright enough to outshine galaxies for days. From that flash come treasures, elements heavier than iron, silver, gold, uranium, are forged in the furious storm of particles and energy. The star's heart, now crushed, becomes a neutron star, a sphere no larger than a city, yet so dense that a teaspoon of its matter outweighs a mountain. If the mass is still greater, gravity wins completely, and a black hole forms, a well in space so deep that not even light can escape. Around it, debris swirls and glows, and from the wreckage, new clouds will someday coalesce. Death feeds birth. Silence becomes light again. Our own sun will never know such violence. It will die quietly, swelling, shedding, fading into a small white ember. But even that soft ending carries purpose. The gases it releases will blend with interstellar clouds, adding a faint shimmer of carbon and oxygen to the galaxy's breath. Perhaps billions of years from now, those atoms will gather again, becoming part of a new star, a new planet, another being looking up into a sky filled with old light. In this way, every star is both a beginning and an ending. Mass sets the tempo, metallicity colors the tone, companions add harmony. The smallest burn forever, the largest vanish in brilliance. And yet each plays its part in the universe's quiet symphony, a rhythm of collapse and creation, of energy becoming form and form becoming dust. Listen closely. This rhythm is not distant. The breath in your lungs, the calcium in your bones, the iron in your blood, all of it was once inside a star. You are not separate from the cosmos, but written in its same glowing ink. The universe is not above you, but within you, moving and remaking itself in every beat of your heart. So rest now. Let that truth hum softly in the space between your thoughts. The stars will keep their watch, shining in their long, patient way. And you, small, luminous, and temporary, belong entirely to their story. In the high blue silence of Orion's belt, a star called Alnilam burns with a brightness too fierce to last. It is one of the most massive kinds of stars the universe can make, more than 40 times the mass of our sun, and it will never know the gentle crimson light of a red supergiant. Stars like Alnilam lose their outer layers so quickly, their winds tearing away oceans of gas each second, that they transform into something rare, a Wolf-Rayet star. In their spectra, astronomers see not the usual fingerprints of hydrogen, but deep, glowing lines from heavier elements, carbon, nitrogen, oxygen, dredged up from within by storms of convection. Their own light has peeled them bare. When helium finally runs out in their cores, gravity takes command again. The center contracts, temperature rises, and heavier fuels ignite one after another: carbon, neon, oxygen, silicon, each burning in its turn, each stage shorter than the one before, until the core becomes an iron heart that can go no further. Iron is the still point of nuclear alchemy. Fusing it consumes energy rather than releasing it. The star, robbed of support, begins to die. In some of these enormous suns, instability comes even earlier. A few are known as luminous blue variables, giants, that pulse and erupt, shedding vast clouds of matter into the dark. Their outbursts can brighten them a millionfold, mimicking supernovae without true destruction. Astronomers call them supernova imposters. Eta Carinae is the most famous. In the 19th century, it flared so brilliantly that sailors could read by its light. Its surrounding nebula still glows from that storm. As the end approaches, the core shrinks and hardens, while the outward radiation grows ferocious, pushing the star's surface away in rippling shells. These layers drift into space as luminous veils, forming what we call planetary nebulae. What remains behind depends on how heavy the leftover core is. If the core's mass is less than about 1.4 times that of the Sun, collapse stops when electrons pack themselves so tightly they can move no closer. The result is a white dwarf, small as Earth, dense as thought, its matter in an exotic quantum state called electron degeneracy. No further fusion burns there. It simply glows, slowly cooling for billions of years, until it becomes an invisible ember, a black dwarf, in a universe too old to exist yet. But when the dying star is more massive, the finale is far louder. As the iron core grows beyond that same limit, gravity crushes it with unstoppable force. Electrons and protons merge into neutrons, releasing a blizzard of neutrinos and a shock wave that rips outward. The explosion, A supernova outshines entire galaxies for days. In our own Milky Way, such events have been seen by human eyes. Brilliant new stars appearing suddenly in the night, blazing for weeks before fading into dust. The remnants of one, seen in 1054 AD, became the Crab Nebula, a ghostly cloud still expanding at thousands of kilometers per second. What's left at the center depends again on weight. If the core is under about 3 or 4 solar masses, it becomes a neutron star, a city-sized sphere where matter is packed so densely that a teaspoon would weigh as much as a mountain. Some spin so rapidly that beams of radiation sweep through space like lighthouse beams. We call them pulsars. Others feed on nearby gas, glowing fiercely in X-rays. But if the core exceeds that mass, gravity deepens past all rescue. Light itself cannot escape, and a black hole is born, not an object, but a region of space where the rules of time and distance fold inward. The collapse is absolute, yet the legacy is creation. Heavy elements, shock waves, and sculpted clouds that will one day give rise to new stars. The deaths of stars are gifts to the cosmos. The debris of supernovae sows the interstellar medium with carbon for life, iron for planets, and gold for wonder. Their radiation stirs surrounding gas into motion, shaping new nebulae, and their pressure sparks new waves of birth. Out of destruction, balance returns. When two stars share their lives, the story grows even more intricate. In a close binary, as one star swells into a red giant, its outer layers can spill toward its partner's gravity. Matter streams from one to the other, creating dazzling variations. Contact binaries that share an envelope, cataclysmic variables that flare unpredictably, blue stragglers that appear young again after merging with their companions, and even Type Ia supernovae, whose explosions serve as cosmic distance markers. In some binaries, this exchange produces paradoxes. The star that looks younger may actually be the elder, stripped and renewed by loss. About half of all sun-like stars live in pairs. For the more massive ones, almost all do. These interactions help explain how some stars evolve faster, shed their shells sooner, or die in ways that solitary stars cannot. Many astronomers believe that binary partnerships are responsible for creating luminous blue variables, Wolf-Rayet stars, and some of the most powerful supernovae we have ever observed. A single star could not rid itself of mass so efficiently, but in a binary, gravity provides both the knife and the sculptor's hand. Yet stars rarely stay just in pairs. They gather in families, clusters of hundreds, thousands, even millions. Every galaxy is a vast city of stars, gas, and dust. Our Milky Way holds around 400 billion suns. Across the universe, there are perhaps 2 trillion galaxies, each one a swirl of its own citizens. Between them drift orphan stars, cast loose by gravitational tides, shining quietly through the void. There are more stars than there are grains of sand on all of Earth's shores, each one a fire keeping its own time. Some of these fires come in intricate arrangements, triple systems, where 2 stars orbit close together, while a third circles farther out, or quadruples in nested hierarchies. Even larger groups form open clusters, where dozens or thousands of young stars drift loosely bound, or globular clusters, dense ancient spheres of hundreds of thousands of suns. The stars within a cluster share the same age and chemistry siblings born from a single collapsing cloud. Many scientists now think most stars began life this way, in clusters or pairs, though most eventually wander apart. In the smallest stars, companionship is rarer. Only about a quarter of red dwarfs have partners, yet red dwarfs themselves make up about 85% of the Milky Way's population. So most of the lights we see or don't see are solitary red dwarfs, quietly shining for trillions of years, unnoticed in the great dark sea. Still, a 2017 study of the Perseus molecular cloud suggested something poetic, that nearly all stars may begin as twins, born side by side, with some later drifting away. Even the loneliest stars may once have had a companion. The nearest star to us, apart from the Sun, is Proxima Centauri, a faint red ember, only 4.24 light-years distant, roughly 40 trillion kilometers. To travel there at the speed of the old space shuttle, 8 kilometers per second, would take about 150,000 years. That gulf of space is typical between stars in the quiet lanes of the galactic disk, in the crowded hearts of galaxies, or in tight globular clusters. Stars can huddle thousands of times closer. Out in the halos that surround galaxies, the opposite is true. The distances stretch so vast that each star may shine in almost perfect solitude. Because space is mostly emptiness, collisions between stars are extraordinarily rare, but in the dense cores of clusters, gravity sometimes pulls two together. When they merge, they create what astronomers call blue stragglers, stars that glow hotter and younger than the company they keep. They are, in a sense, reborn, appearing to rewind their clocks through collision or exchange. The weight a star inherits at birth determines nearly everything: its brightness, color, temperature, how long it will shine, and how it will die. Most of the stars we see today are between 1 and 10 billion years old, yet some are nearly as ancient as time itself. The oldest known, HD 140283, the Methuselah star, has lived for about 14 billion years, give or take a billion, a reminder that even in our measurements of the cosmos, there is room for mystery. Mass is destiny. The heavier the star, the shorter the life. A giant lives for only a few million years before burning out in glory. A tiny red dwarf will glow for hundreds of billions, long after the universe has dimmed. The heavens we look upon tonight are therefore a layered portrait of time, some stars newly born, some long dead, but their light still crossing the dark toward us, each one a note in a song that began before memory. And somewhere, across those impossible distances, the dust of ancient supernovae is still drifting, still cooling, still folding itself into clouds that will collapse once more. From those clouds, new stars will rise, new worlds will form, and new eyes will look up in wonder. The cycle continues, matter to light, light to dust, dust to life, the quiet, ceaseless rhythm of the universe, breathing itself awake. When new stars awaken in the Milky Way today, they are made mostly of the same simple ingredients that have built the cosmos since its beginning, about 71% hydrogen, 27% helium, and only a whisper of heavier elements. That small fraction, though, makes all the difference. Astronomers call it metallicity, and often measure it by the presence of iron, whose spectral signature is bright and easy to see. A star rich in iron and other heavy elements was likely born from material recycled many times ashes of older generations. Such stars are also more likely to cradle planets, small worlds spun from that enriched dust. Some stars, however, are nearly pure, almost untouched by cosmic history. One faint star, He 1327 to 2326, carries only 1/200,000th of the sun's iron. Others, like Mu Arai or 14 Hercules, are heavy with metals 2 or 3 times richer than the Sunday. Their chemistry speaks of long ancestry and fertile potential. A few, called chemically peculiar stars, bear odd mixtures of elements such as chromium or rare earth metals, shaped by magnetic fields or internal currents. Cooler stars, including our own sun, harbor molecules in their outer layers: carbon monoxide, water vapor, titanium oxide, fragile things that can exist only in the gentler temperatures near the surface. From Earth, all these suns appear as tiny, trembling points. The twinkling we see is not in the stars, but in our air, light bending through the restless shimmer of the atmosphere. Only the sun, close and warm, shows its shape, a disk too bright to look upon. The next largest in our sky, R Doradus, is still so small in apparent size, a mere 0.057 arcseconds, that even telescopes see it as a speck. To measure such distant orbs, astronomers use delicate methods: interferometry, which joins light from multiple telescopes to act as one giant eye, or occultation, timing the instant a star slips behind the moon's edge to infer its diameter. The true scale of stars defies the imagination. The smallest remnants, neutron stars, are only about 30 kilometers wide, tiny spheres of crushed matter left from supernovae. The largest, supergiants, like Betelgeuse and Orion, would engulf our entire solar system if placed at its center, spreading 600 times wider than the sun, their densities thin as smoke. Between these extremes lies the grand diversity of stellar life, from modest dwarfs to swollen titans, each burning according to its mass and age. Stars move, too, drifting through the galaxy on their own long paths. Astronomers describe these motions in 2 ways. The radial velocity measures how fast a star moves toward or away from us, revealed by the Doppler shift in its light. The proper motion is its sideways drift across the sky, so slow that it must be measured in thousandths of an arcsecond per year. By combining these, scientists can trace a star's true journey through space. Nearby stars usually show the quickest motions, while those far away glide more subtly, their changes stretching across centuries. The youngest, metal-rich population I stars travel in calm, circular orbits around the Milky Way's center. The older, metal-poor population II stars cut steeper, more tilted paths, relics of an earlier galactic shape. By following their motion, astronomers can sometimes trace them back to their birthplaces, clusters, and associations that were once single clouds of gas and dust. Even after the cluster disperses, the family resemblance remains in their shared direction, a faint memory of origin. Inside each star, another invisible movement stirs: convection. The rolling, boiling motion of hot plasma turns the interior into a natural dynamo, generating magnetic fields that reach far beyond the surface. The faster a star spins, the stronger this magnetic force becomes. It manifests in star spots, dark, cooler blotches, where the field knots the flow of energy, and in arcs of glowing plasma called coronal loops, arching high into the star's atmosphere. Occasionally, the tension snaps, releasing flares and storms of charged particles. These outbursts are both violent and beautiful, magnetic lightning across the face of eternity. Young stars rotate quickly, their magnetic fields tangled and fierce, producing constant flares. But time is a patient sculptor. Over millions of years, the magnetic field itself acts as a brake, coupling with the stellar wind to slow the spin. Old stars, like our sun, turn more slowly and live more quietly. Yet even the sun has moods. Every 11 years or so, it moves through a cycle of rest and activity, its surface spotted with dark storms and then cleared again. There are longer rhythms too. During the 1600s and early 1700s, in what astronomers call the Maunder minimum, the sun fell nearly silent for 70 years, its surface calm, its light steady and pale. Across the sky, stars vary in size and weight beyond anything we can easily imagine. Some are less than half the sun's mass, glowing softly for trillions of years. Others, like Eta Carinae, tip the scales at more than 100 suns, raging through their brief lives in only a few million years. Observations suggest there is an upper limit to how large a star can grow, around 150 solar masses. Beyond that, radiation pressure becomes too fierce, blowing away the very gas that tries to fall in. Yet, the universe loves exceptions. In the R136 cluster, deep within the Large Magellanic Cloud, astronomers have found giants even larger, perhaps the result of two massive stars merging, briefly outwitting nature's restraint. The very first stars that ever burned the long-vanished Population 3 were stranger still. Born from the raw hydrogen and helium left by the Big Bang, they contained no heavy elements at all. Without those impurities to cool them, they could grow enormous, perhaps 300 times the sun's mass. They lived fast, burned bright, and died young, flooding the newborn cosmos with the first heavy elements, setting the stage for everything that would follow: planets, oceans, life, thought. Their light no longer reaches us directly, but its echo lingers in the chemistry of everything we are. In 2015, astronomers glimpsed a hint of such ancient fire in a distant galaxy known as Cosmos, Redshift 7, seen as it was when the universe was only a fraction of its present age. The light that reaches us from there began its journey more than 13 billion years ago, before Earth, before the Sun, before even the Milky Way had finished taking shape. It travels still, a faint whisper through time, reminding us that every star, no matter how distant, is part of one continuous story: hydrogen and gravity learning, over and over, how to shine. At the smallest edge of the stellar world, where gravity just manages to light the first faint spark of fusion, lies a tiny sun called 2 Mass J 523-1403. It's barely a star at all, only 80 times the mass of Jupiter, the minimum needed for hydrogen to begin burning. Below that, gravity can squeeze and warm, but not ignite. This boundary between almost star and true star depends on composition. With fewer heavy elements, a star must be slightly larger, around 8% the mass of our Sun, to cross that invisible threshold. Anything smaller falls into the in-between realm of brown dwarfs, too massive to be called planets, too light to sustain nuclear fire. They glow softly from leftover heat, fading slowly into obscurity, failed suns dreaming of what they might have been. The strength of a star's gravity depends on its size and mass. A red supergiant, spread thin across millions of kilometers, holds its outer layers gently, while a white dwarf or neutron star compresses matter so tightly that gravity becomes overwhelming, crushing, absolute. This invisible pressure even leaves traces in the star's spectrum. The stronger the gravity, the broader the absorption lines appear, like fingerprints pressed deeper into glass. Stars also differ in their speed of spin. Some whirl with dizzying haste, their equators racing faster than the eye can imagine. Astronomers can read this rotation in the stretched and blurred patterns of a star's spectrum, or by watching the movement of dark star spots across its surface. Young stars often spin at 100 kilometers per second or more. The blue star, Achernar, for instance, spins so fast, about 225 kilometers per second, that it bulges outward, its equator 50% wider than its poles. A little faster, and the star would fly apart entirely. Our Sun, by contrast, turns with grace and leisure, completing a rotation every 25 to 35 days, its equator moving at less than 2 kilometers per second. With age, most stars slow down. Their magnetic fields interact with their stellar winds, creating a subtle braking force that tugs against their rotation. But when a star dies and collapses into something smaller, the story changes again. A white dwarf, or neutron star, shrinks enormously, conserving some of its spin. The smaller the size, the faster it turns. Pulsars, the spinning remnants of supernovae, are the ultimate examples. The one in the Crab Nebula rotates 30 times every second, a whirling core of atomic matter flashing radio waves through space. Over time, even these frantic rotations fade, as the star's energy slowly bleeds away into the cosmos. Temperature is another measure of a star's inner life. On the main sequence, the long middle years of its existence, a star's temperature depends on how much energy is produced in its core and how large its surface is. Astronomers estimate it using color, since heat and hue are intertwined. Hotter stars shine blue-white, cooler ones glow orange or red. The effective temperature they calculate is an idealized number, the temperature that a perfect black body would have if it radiated the same amount of energy. Beneath that surface, the heat climbs steeply. In the core, millions of degrees press atoms together until fusion begins. Fusion is the star's secret engine, the merging of light atoms into heavier ones, each reaction releasing tiny quanta of energy that, multiplied by trillions, become the light of the heavens. As that energy journeys outward, it changes form, gamma rays turning to visible light, to ultraviolet, to the warmth that reaches a distant world. The color we see is the outer expression of that deep internal fire. The hottest O-type stars blaze at 50,000 Kelvin, while a yellow star like the Sun rests around 6,000. Red giants are cooler still, their glow soft but vast, their surfaces stretched thin across immense distances. Stars shine across the entire electromagnetic spectrum, not just in visible light, but also in radio waves, infrared, ultraviolet, X-rays, and even gamma rays. Each wavelength tells a different part of the story. Radio signals reveal the magnetic fields, infrared traces the cooler dust around them, ultraviolet shows the heat of newborn stars, X-rays whisper of violent flares and collisions. By reading the full spectrum, astronomers can uncover a star's chemistry, gravity, spin, and even age. If distance is known, often measured through parallax, the subtle shift in a star's position as Earth orbits the Sun, then its luminosity, or total power output, can be calculated. With luminosity, temperature, and spectrum, the rest unfolds. Mass, radius, gravity, rotation, and sometimes even history. In binary systems, where two stars orbit each other, mass can be measured directly through motion. And in rare cases, the bending of light by gravity microlensing allows astronomers to weigh a single, isolated star. A star's luminosity depends mainly on its size and surface temperature, but its light is rarely uniform. Some stars spin so fast that their poles are hotter and brighter than their equators, as in Vega, which glows more fiercely at the top than around its middle. Others have cooler patches called star spots, darker islands where magnetic fields choke the flow of energy. On small stars, these are subtle freckles. On giants, they can sprawl across continents of plasma. Often, the edges of a star appear dimmer than its center, an effect called limb darkening, caused by looking through cooler, shallower layers at the rim. The brightness we see from Earth is called apparent magnitude, a mix of true luminosity, distance, and the dimming effects of interstellar dust and atmosphere. To compare stars fairly, astronomers use absolute magnitude, how bright the star would appear if it were exactly 10 parsecs, or 33 light-years, away. Through all these measures, color, temperature, brightness, a pattern emerges. Early in the 20th century, astronomers began to classify stars by their spectra. At first they labeled them A through Q, thinking hydrogen's absorption line grew stronger with temperature. But nature's order was subtler. Hydrogen's line peaks around 9,000 Kelvin, then weakens again in hotter stars. So the system was reshuffled into the sequence we still use today: OB, A, F, G, K, M. A rhythm that moves from the blue-white blaze of the hottest stars to the deep red warmth of the coolest. Our Sun, steady and familiar, is a G-type star, balanced between extremes, not the biggest or the brightest, but a gentle middle light, perfect for life to gather around. In the end, each star, from the smallest brown dwarf to the largest supergiant, is a different expression of the same cosmic principle: gravity drawing matter inward, pressure pushing outward, energy finding its way to shine. Their colors and temperatures, their spins and pulses, all speak of this one quiet law. In every corner of the universe, where hydrogen is gathered and held close enough, light is born. Across the vast scale of heat and light, every star is given a name, made of a single letter, a soft shorthand for temperature, color, and the shape of its fire. From O to M, the sequence runs like a cosmic melody. O, blazing blue and hot; B and A, bright white; F and G, golden like our sun; K and M, orange and red, cool and calm. Beyond these, at the edge of starlight, are L and T, faint brown dwarfs, where warmth flickers more than it burns. Each letter divides into 10 finer notes, from 0 to 9. The sun sits serenely at G2, neither fierce nor faint, a perfect middle flame. At the upper extremes, the pattern phrase stars as hot as O0 may not exist at all, their heat beyond even the alphabet's reach. Stars are also sorted by size and surface gravity, the quiet weight pressing inward and the pressure pushing back. Main sequence stars, like our Sun, are class V, giants are 3, supergiants, white dwarfs, live in their own class, V. On the great chart of luminosity and temperature, the Hertzsprung-Russell diagram, these stars fall along a diagonal river of light. The Sun's address, G2V, marks it as a yellow dwarf, modest and long-lived. Small details decorate the code: E for emission lines, M for metal-rich, VAR for a shifting spectrum. Even white dwarfs, the dim embers of dead suns, have their own set of letters: DA, DB, DO, DZ, DQ, their light, whispering what elements still glow within. But stars are not always steady. Many pulse, flare, or fade with time. Variable stars are living rhythms. Cepheids swell and contract like slow heartbeats. their brightness rising and falling in precise intervals, their pulse so consistent that astronomers use it to measure the size of the universe. Others erupt without warning, young stars and wolf-rayet giants that shed their skins in brilliant storms. In certain binaries, when a white dwarf steals gas from its partner, the theft ignites a runaway fusion that flares across space, a nova, or in rarer cases, a supernova. Even gentle changes can create drama. In the eclipsing system of Algol, one star hides the other every 2.87 days, causing its light to dip and return, like breathing in the dark. Inside every calm star is a perfect balance, gravity pulling inward, pressure pushing outward, a state called hydrostatic equilibrium. Deep within, the core burns with a temperature of millions of degrees, fusing hydrogen into helium. Each reaction releases energy as gamma rays, which scatter through the dense plasma, losing strength, transforming as they climb. The light that escapes from the surface tonight may have begun its journey millions of years ago, born in the silence of fusion. As hydrogen turns to helium, the star's core thickens and contracts, while new burning begins in shells around it. Yet through it all, the flow of heat remains even the same amount, leaving each layer, as enters it, the steady breath of stellar life. The way energy travels depends on what the star is made of. In calm, transparent regions called radiation zones, light moves slowly outward, absorbed and re-emitted in endless succession. But if the heat builds too fast or the gas grows too thick, the stillness breaks into motion. Hot plasma rises, cooler plasma sinks, and convection begins a churning ocean of fire. In massive stars, convection happens deep within, while the outer layers remain quiet and radiative. In stars like the Sun, the core radiates and the outer layers boil. The smallest red dwarfs mix completely from core to surface, turning their fuel so efficiently that they may burn for trillions of years. What our eyes see, the bright surface where light finally escapes, is the photosphere, a thin, trembling boundary between star and space. Here appear the dark scars of sunspots, magnetic storms that twist the flow of plasma. Above lies the chromosphere, where narrow jets leap upward like glowing threads, and flares burst in sudden fury. Just beyond it, in a thin layer only 100 kilometers thick, the temperature leaps thousands of times higher, the mysterious transition region, and then opens into the corona, a great pale crown of plasma reaching millions of kilometers outward. It is faint, hotter than the surface below, and visible only during a total eclipse. From this shimmering halo flows the stellar wind, a ceaseless stream of particles. Around our sun, that wind carves out a vast invisible bubble, the heliosphere that extends far beyond Pluto, a quiet frontier between solar breath and interstellar air. All this radiance comes from the simplest act in the universe, matter becoming energy. When atoms fuse, a sliver of mass vanishes, transformed into light, according to Einstein's E equals mc squared. A teaspoon of such transformed matter could power a city for years. In small red stars, fusion burns at around 4 million Kelvin. In the hearts of giant blue suns, it blazes at 40 million. The sun's own furnace glows at 16 million Kelvin, slowly weaving helium from hydrogen through the proton-proton chain. In stars far heavier, fusion becomes more elaborate, cycling through carbon, nitrogen, and oxygen, then burning neon, oxygen, silicon, until it reaches iron, the end of the line. Iron cannot release energy through fusion. It is the still point of nuclear fire. When enough of it builds in a massive star's heart, Gravity wins at last. The core collapses in a heartbeat, and the energy that once held the star together bursts outward. A supernova is born, a single flare of light, bright enough to outshine a galaxy. And in that brief, magnificent death, the universe renews itself, scattering the seeds of everything that will ever live or shine again. A galaxy is a vast city of light, a boundless architecture of stars, gas, dust, and something darker still, the unseen weight we call dark matter. Gravity is its mason and its law, binding everything together in a slow, silent dance that has lasted for billions of years. Some galaxies hold only 1,000 stars, small and quiet as a village at dusk. Others are sprawling metropolises of light, home to trillions of suns. But what we can see, the bright points and glowing clouds, is only a fraction of what is really there. Most of a galaxy's mass lies hidden in shadow, invisible but present, its pull felt across vast reaches of space. At the hearts of many galaxies where gravity is strongest, enormous black holes rest, engines so dense that even light cannot escape their grasp. Around them, the stars orbit like sparks circling a dark flame. The Milky Way, our own galactic home, carries such a heart as well, a supermassive black hole called Sagittarius A*, veiled in dust and radio whispers. Astronomers sort galaxies by their shapes the way starlight gathers and swirls. Elliptical galaxies are smooth, luminous ovals of ancient stars. Spiral galaxies unfurl in grand arms of dust and color, sweeping outward from a bright core, like seashells or whirlpools. The Milky Way is one of these, a barred spiral seen from within, its arms like rivers of light flowing through cosmic night. And some galaxies refuse all order, irregular in shape, chaotic, scarred by collisions or tidal forces, their beauty found in disorder. Across the universe, galaxies fill the dark like lanterns scattered over an infinite sea. Astronomers estimate their number between 200 billion and 2 trillion, each one a continent of suns, each one impossibly far from its neighbors. They range in size from a few thousand to hundreds of thousands of light years across, and the gulfs between them are measured in millions of light years. Our Milky Way stretches roughly 87,000 light years wide and drifts about 2.5 million light years from its great neighbor, the Andromeda Galaxy. Even the spaces between galaxies are not empty. They are threaded with a ghostly mist called the intergalactic medium, thinner than any vacuum made on Earth, containing fewer than 1 atom in a cubic meter. Galaxies gather together into families, groups, clusters, and superclusters, each one a gravitational web of thousands of members. Our Milky Way and Andromeda belong to the local group, which itself drifts inside the much larger Virgo supercluster, and beyond that, all are part of an even grander tapestry called Laniakea, the immense heaven, a word borrowed from Hawaiian. In the cosmic map, these superclusters are strung together like threads of light, surrounding vast, dark voids, forming a structure called the cosmic web, a universe woven rather than scattered. Over the centuries, astronomers have cataloged millions of galaxies, though only a handful carry names that sound familiar to human ears. Andromeda, the Magellanic Clouds, the Sombrero Galaxy, the Whirlpool. The rest are known by numbers, quiet entries in the sky's long ledger. Yet even before telescopes and charts, people had wondered what the pale band of the Milky Way really was. In ancient Greece, the philosopher Democritus imagined that it might be made of countless distant stars, their light blurred into one. Aristotle disagreed. He thought it was a kind of atmospheric fire, born from vapors near the edge of Earth's air. Centuries later, Olympiodorus the Younger argued that the Milky Way must lie beyond the sky because it never changed shape no matter where one stood. In the Islamic Golden Age, scholars took these questions further. The scientist Ibn al-Haytham, living 1,000 years ago, tried to measure the Milky Way's distance by looking for parallax, the tiny shift that nearby objects show against distant ones as Earth moves. He found none, and concluded that it must lie far beyond the atmosphere. Al-Biruni, Avicenna, and later Ibn Qayyim al-Jawziyya described it as a vast congregation of stars whose blended light made the night glow like mist. Real proof came with Galileo, who in 1610 turned his telescope toward that hazy band and found it made of innumerable faint stars, too many to count, shining together as one. By 1750, Thomas Wright suggested that the Milky Way was a great rotating system, held together by gravity, like a solar system on a grander scale. Immanuel Kant went further, proposing that the faint nebulae seen in the sky might be other such star systems, other galaxies. In 1785, William Herschel began mapping the Milky Way by counting stars in every direction. He pictured our sun near the center of a vast disk of light. Later, Jacobus Kapteyn refined the idea, imagining an ellipsoid shape. Around the same time, Harlow Shapley, studying globular clusters, discovered something extraordinary. The Milky Way was far larger than anyone had guessed, and the sun was not in its center, but out toward the edge. Both men were right and wrong in part, for they could not yet account for the dimming effect of interstellar dust. That correction came in 1930 from Robert Trumpler, who showed that dust veils the light of distant stars and hides the Milky Way's true size. Since then, our view of the galaxy has deepened beyond even their dreams. We now know that it is a spiral island of more than 400 billion stars, each orbiting slowly around a dark heart. The arms of the Milky Way curve through space like great luminous rivers, and from a quiet place on Earth, far from city lights, you can still see their reflection. On a clear night, that soft white band across the sky is not mist or cloud, but the combined light of countless suns, each a spark in the grand city of our galaxy, each whispering through the dark. You are part of this too. Over 1,000 years ago, when the night skies of Persia were still untouched by the glow of modern cities, the astronomer Abd al-Rahman al-Sufi looked up and saw a faint blur in the darkness, a small cloud, he wrote in his book of fixed stars. That cloud was the Andromeda Galaxy, though no one yet knew what a galaxy truly was. In that same work, written in 964, he also noted another distant mist, what we now call the Large Magellanic Cloud, a ghostly glow that lies far to the south, beyond the reach of his northern eyes. Centuries later, when Ferdinand Magellan's ships crossed the southern seas, European sailors saw this same shimmering patch and gave it his name, not knowing it was a neighboring galaxy filled with hundreds of billions of suns. In 1612, Simon Marius, a German astronomer, made his own record of the Andromeda Galaxy, confirming its place among the catalogue of wonders. A century later, thinkers began to stretch their imagination beyond the stars. In 1734, the Swedish philosopher Emanuel Swedenborg suggested that space might hold not just one system of stars, but many vast cosmic clusters far beyond our own. The idea was daring for its time, a whisper of the truth that modern astronomy would later confirm. Soon after, Pierre-Louis Maupertuis suggested that the misty patches in the sky were not single clouds, but immense gatherings of stars, their light blending together like the glow of a city seen from afar. Thomas Wright of England went further in 1750, proposing that the Milky Way itself was a great flattened disk of stars, and that other hazy nebulae might be distant Milky Ways of their own, islands of light adrift in the sea of darkness. By the late 1700s, astronomers began to map the heavens in earnest. Charles Messier, searching for comets, catalogued 109 faint, cloud-like shapes, the Messier objects still known today. William Herschel later expanded this list to over 5,000, each one a mystery waiting for understanding. In 1845, Lord Rosse, using a powerful new telescope, observed one of these, Messier 51, and discovered its spiral shape, what we now know as the Whirlpool Galaxy. The 20th century turned speculation into revelation. In 1912, Vesto Slipher studied the light from spiral nebulae and found that many were racing away from us at tremendous speeds, hinting that they might lie far beyond our galaxy. A few years later, Heber Curtis observed a nova inside the Andromeda Nebula and realized it was astonishingly faint compared to those within the Milky Way. From this, he inferred that Andromeda must lie far beyond our galactic borders, an island universe, as he called it. This radical idea led to the great debate of 1920 between Curtis and Harlow Shapley over whether the Milky Way was the entire universe or merely one among countless others. Curtis argued that the spirals were separate galaxies, supported by their dust lanes and spectral shifts. 2 years later, the Estonian astronomer Ernst Öpik confirmed this view with careful calculations. And then came Edwin Hubble, who in 1924, using the great 100-inch telescope at Mount Wilson, resolved individual stars in Andromeda and found Cepheid variables whose pulsations revealed their immense distance. The universe, once thought to end with the Milky Way, suddenly expanded into infinity. Hubble went on to classify galaxies by their shapes, spirals, ellipticals, and irregulars, a system still used today. Yet even as we named and mapped the stars, we had seen only through one narrow window, visible light. In the decades that followed, astronomers began to explore the rest of the spectrum. Infrared telescopes revealed the hidden nurseries where stars are born, their glow filtered through veils of dust. Radio waves exposed invisible structures, enormous jets streaming from galactic cores, and the soft whisper of hydrogen gas spread between the stars. In 1944, Hendrik van de Holst predicted that hydrogen atoms would emit a specific radio signal at a wavelength of 21 centimeters. In 1951, astronomers detected it exactly as he described. This faint radio light, passing unhindered through interstellar dust, allowed us to trace the spiral arms of our own galaxy, revealing for the first time its bar-shaped heart. Then came Vera Rubin in the 1970 seconds, measuring how stars moved within galaxies. She discovered something that changed everything. The outer stars were orbiting far too quickly. There wasn't enough visible matter to hold them in place. The galaxies should have been flying apart, but they weren't. The only explanation was an invisible mass, a great unseen scaffold holding galaxies together. It became known as dark matter, a name for something we still cannot see but can feel in the pull of every star. As telescopes grew sharper, our understanding grew deeper. The Hubble Space Telescope, launched in 1990, looked beyond Earth's turbulent air into the cold clarity of space. Its deep field image, a long, patient stare into what seemed like nothing, revealed that even the darkest corners of the sky are filled with galaxies, hundreds of billions of them, each one a universe in itself, each one containing worlds we will never see. Other eyes soon joined Hubble's infrared observatories, radio telescopes, and X-ray satellites that saw the hidden cosmos, the galaxies shrouded by dust, the jets of matter from black holes, the glow of clusters filled with million-degree gas. X-rays traced the signatures of supermassive black holes, silent giants, millions or billions of times heavier than the Sun, lying at the hearts of nearly every galaxy. By 2016, a team led by Christopher Kinselis used deep space data to estimate that the observable universe might contain 2 trillion galaxies, 10 times more than previously thought. Yet, when NASA's New Horizons spacecraft, sailing beyond the Sun's glow, measured the faint background light of the universe, it found less than expected. Perhaps there are fewer galaxies than we once believed, or perhaps the smallest, faintest ones still hide in the shadows, their light too weak to reach us. Either way, the truth remains humbling. The universe is deeper and richer than any human mind can fully imagine. Every faint blur seen through a telescope, every distant smudge of light on a photographic plate is another island of suns, each with its own history, its own motion, its own mysteries. And when we look up from our quiet corner of the Milky Way, what we see is not emptiness at all, but a living ocean of galaxies drifting together through the endless dark. Galaxies, those immense, glowing cities of stars, come in many forms, each shaped by gravity's slow and ancient art. Astronomers often group them into 3 main families: elliptical, spiral, and irregular. The classification was first mapped by Edwin Hubble, whose tuning fork diagram arranged the heavens by shape, like an artist sorting brushstrokes. But the beauty of galaxies cannot be captured by geometry alone. A galaxy's spirit lies not only in how it looks, but in how it lives, in how quickly it gives birth to new stars, how much dust it breathes, and how fiercely the heart within it burns. At the center of nearly every galaxy, astronomers have found something extraordinary: a supermassive black hole, a region of gravity so intense that nothing, not even light, can escape. Our own Milky Way carries such a heart, a dark mass millions of times heavier than the Sun, hidden behind clouds of dust at its core. Elliptical galaxies are among the most ancient and tranquil. In Hubble's scheme, they range from round E0 forms to stretched E7 shapes, smooth and featureless like marbles of light. They hold little gas or dust, and so few new stars are born there. Instead, they glow faintly with the long, steady light of old suns, ancient, metal-poor stars drifting on random paths around a common center. These galaxies are like vast mausoleums of starlight, quiet, settled, and old. Some ellipticals grow beyond imagination into supergiant elliptical galaxies, or CD galaxies, titans of the cosmos, first recognized in the 1,960 seconds. These behemoths, often found at the hearts of galaxy clusters, possess dense cores wrapped in halos that stretch across millions of light years. Their light fades slowly outward, like mist around a distant lamp. Scientists believe they are born from countless galactic mergers as smaller galaxies fall together under gravity's pull. In time, they blend into one immense structure, surrounded by a faint cloud of orphaned stars, the remnants of cosmic cannibalism. In clusters such as Perseus or Phoenix, astronomers have found hints of this process continuing still, gas cooling, collapsing inward, and igniting fresh bursts of star formation in the dark. Some ellipticals bear delicate ripples, as if starlight itself had remembered a disturbance. These shell galaxies show thin, curved layers, faint rings like waves spreading across a pond after a stone has fallen. They are the signatures of old collisions, when one galaxy devoured another and their stars, tugged by gravity, settled into rhythmic layers. The galaxy NGC 3923 holds more than 20 of these ghostly shells, frozen echoes of a galactic feast. If ellipticals are the elder statesmen of the cosmos, spiral galaxies are its dancers, radiant, restless, full of motion. Their bright arms curl outward from a luminous center like ribbons of light. Most of the stars and gas lie within a flat rotating disk, yet far beyond the visible edge, an invisible halo of dark matter holds them together. Without it, their arms would fly apart. The pattern of their rotation, known as the universal rotation curve, offers some of the strongest evidence that dark matter is real. Each spiral has three main parts: the glowing bulge of older stars at its core, the rotating disk filled with gas and dust, and the spiral arms, regions of crowding and compression, where gravity gathers material and triggers the birth of new stars. In Hubble's system, spirals are labeled SA, SPI, or C, depending on how tightly their arms curl and how large the bulge appears. The SAW types are neat and conservative, their arms faint and close. C galaxies are looser, flamboyant, their arms open and radiant. Some are flocculent, patchy, and irregular, while others, the grand designed spirals, display a perfect symmetry that seems drawn by an invisible hand. The arms themselves are not permanent structures. They are density waves, slow-moving traffic jams of stars and gas that drift through the disk. As clouds of hydrogen pass through these waves, they are squeezed, collapse, and ignite, giving birth to blue, hot stars whose short lives illuminate the arms. The stars move on, but the wave remains, sweeping around the galaxy in endless procession. Many spirals, including our own Milky Way, possess a bright bar of stars, cutting through their centers, a kind of stellar bridge connecting the inner bulge to the outer arms. Bars form when gravitational waves or nearby galaxies disturb a spiral's equilibrium. Over time, the bar funnels gas inward, feeding the core and sometimes awakening the sleeping black hole within. The Milky Way is one of these barred spirals, about 100,000 light-years wide and 3,000 thick, home to roughly 200 billion stars and the traces of many more yet unseen. Some spirals grow so large and brilliant that they earn a separate name: superluminous spirals. Stretching nearly 500,000 light-years across, 5 times the size of the Milky Way, they blaze with ultraviolet fire and form new stars at a furious pace, 30 times faster than our galaxy's gentle rhythm. They are the cosmic equivalents of starburst cities, burning bright and living fast. Not every galaxy fits so neatly into this order. Some are strange, twisted, or misshapen, sculpted by collisions. A ring galaxy, for instance, forms when a smaller galaxy plunges straight through the center of a spiral, sending out shock waves that rearrange its stars into a circular bloom. Others, caught in the act of transformation, become lenticular galaxies, smooth disks without distinct arms, halfway between spiral and elliptical. When these have a bar across their middle, astronomers call them barred lenticulars. And then there are the irregular galaxies, which defy all symmetry. Some, called Ur-I, still show faint hints of order, while others, Ur-II, are completely chaotic, the aftermath of gravitational encounters or violent mergers. The large and small Magellanic Clouds, our Milky Way's nearby companions, are such irregular dwarfs, small, distorted, and full of new stars. More mysterious still are the dark galaxies, enormous but faint, their light dimmed almost to invisibility. They may be as large as the Milky Way, but shine with only 1% of its brightness. Perhaps they lost their gas long ago, or perhaps their stars never had the chance to form. What remains are ghost cities of the cosmos, their presence betrayed only by the pull of gravity on the matter around them. Yet in truth, most galaxies are not giants at all. The universe is filled with dwarf galaxies, tiny, humble clusters of stars, often only a few billion in number. Some, called blue compact dwarfs, shimmer with the light of hot young suns. Others are so small they span barely 300 light-years, containing just a few million stars pressed together like grains of light. Many of these dwarfs orbit larger galaxies like satellites. The Milky Way alone hosts at least a dozen known companions, and astronomers suspect there may be hundreds more hidden in the dark, circling unseen. Within our local group, these small galaxies reveal a secret that astonishes scientists. Whether they hold a few thousand stars or millions, each seems to possess the same central mass, around 10 million suns. This remarkable consistency suggests that dwarf galaxies are bound and shaped by dark matter, their faint light merely tracing the outlines of a much larger, invisible structure. It also hints that there may be a natural lower limit to what gravity can build, a scale below which even dark matter cannot clump. Some researchers believe this may point to a gentler, warm kind of dark matter, one that moves too swiftly to form tiny knots, smoothing out the smallest galaxies before they can form. Whatever the answer, these dwarfs, faint, ancient, persistent, are like the foundation stones of the universe. From the largest ellipticals to the tiniest dwarfs, from bright spirals to dim ghostly shadows, galaxies tell the story of creation itself, the endless conversation between gravity and light, between what we can see and what we can only feel. They are the architecture of the cosmos, the living handwriting of time upon the dark. Galaxies are not lonely wanderers drifting through an empty void. They live in a restless universe, constantly pulled and reshaped by gravity's long reach. Sometimes they pass near each other like ships in the dark, tugging at one another's stars and gas without ever making contact. These near encounters twist their disks, stretch their arms, and even draw thin bridges of matter between them, faint trails of dust and starlight that betray an invisible handshake across space. When two galaxies meet head-on, the spectacle is far more dramatic. Despite the violence of the encounter, their stars almost never collide. They are far too small and too far apart. But their clouds of gas and dust do crash together, compressing and heating until they ignite a storm of star birth. Collisions like these can sculpt strange new shapes, long tidal tails, glowing rings, and great sweeping arcs of light. Over time, gravity settles the chaos into new forms, sometimes fusing the two galaxies into one. Such galactic mergers are among the grandest events in cosmic history. When two galaxies approach too slowly to pass each other by, they become locked together in a spiraling embrace that lasts hundreds of millions of years. If one galaxy is much larger, it devours the smaller, a process astronomers poetically call galactic cannibalism. The Milky Way itself is in the act of consuming at least two companions right now: the Sagittarius Dwarf Elliptical Galaxy and the Canis Major Dwarf Galaxy, whose stars are being stretched into faint streams that wind around our sky. Galaxies are the birthplaces of stars, their cold clouds of gas serving as cosmic nurseries. When conditions are right, these clouds collapse to form thousands of new suns. Some galaxies undergo such furious bursts of creation that astronomers call them starburst galaxies. They form stars at a rate hundreds of times faster than the Milky Way, burning through their gas reserves so quickly that the frenzy can only last a few million years, the blink of an eye, in cosmic time. These galaxies glow intensely in ultraviolet and infrared light, powered by massive young stars that ionize surrounding gas into brilliant 2-2 regions. As these hot stars die, they explode as supernovae, sending shock waves that compress nearby clouds and trigger yet more star formation, spreading like wildfire across the galactic disk. A famous nearby example is Messier 82, the Cigar Galaxy, which flared into a starburst after a close gravitational encounter with its neighbor, M81. While some galaxies blaze with newborn stars, others are dominated by the strange energies of their cores. Certain galaxies pour out radio waves far beyond their visible edges, creating vast lobes that stretch for millions of light years. These are radio galaxies, powered by jets from the supermassive black holes at their centers. Astronomers classify them into two types: FR1, which are dimmer and more diffuse, and FR2, whose radio lobes are bright and sharply defined. The largest of these cosmic giants, such as Alcyonius, whose lobes span over 16 million light-years, dwarf entire clusters of galaxies. Their jets travel near the speed of light, carving glowing scars in the thin gas between galaxies. At the heart of many galaxies lies an active galactic nucleus, or AGN, a compact engine that can outshine every star around it. Its power comes from an accretion disk, a whirlpool of gas spiraling into the central black hole. As matter falls inward, friction and gravity transform it into radiant energy, unleashing brilliant light across the spectrum. When the inflow is intense, the nucleus becomes a quasar, dazzlingly bright, even from billions of light years away. Astronomers now understand that the different kinds of active galaxies, Seyfert galaxies, radio galaxies, blazars, and quasars are essentially the same phenomenon, seen from different angles or at different stages of activity. In about 10% of AGNs, the black hole's magnetic fields channel twin jets outward at nearly light speed. If one of those jets happens to point toward Earth, we see a blazar, its light amplified by relativistic effects into violent, flickering brilliance. Seyfert galaxies are the quieter cousins of quasars, bright, energetic cores wrapped inside visible host galaxies. They appear ordinary at first glance until a telescope reveals a blinding point of light at their centers. Seyferts are divided into two subtypes, depending on which wavelengths dominate their emission. In contrast, quasars, short for quasi-stellar radio sources, can shine more than 100 times brighter than the Milky Way, their light crossing billions of years to reach us. The nearest known quasar, Markarian 231, lies over 500 million light-years away, while some of the farthest, like UHC-1, formed when the universe was less than 1 billion years old. These distant beacons have also revealed one of Einstein's most beautiful predictions: gravitational lensing. The immense gravity of a foreground galaxy can bend and magnify the light of a background quasar, creating multiple images of the same source or stretching it into elegant arcs. Through these natural cosmic lenses, astronomers can glimpse galaxies too faint or distant to be seen otherwise. Other galaxies host less intense forms of nuclear activity known as liners, short for low ionization nuclear emission line regions. Their cores emit faint radiation dominated by weakly ionized atoms, likely powered by aging stars, shock waves, or small-scale black hole activity. Around a third of all nearby galaxies show signs of liner-type emission, a quiet middle ground between normal and active galaxies. Even more radiant are the luminous infrared galaxies, or LIRGs, which shine with the energy of over 100 billion suns, most of it released as infrared light. Their brilliance comes from both rampant star formation and hidden AGNs, their dust-absorbing starlight and re-emitting it in longer wavelengths. Galaxies even more extreme, known as ultraluminous infrared galaxies, ULIRGs, can outshine LIRGs tenfold, forming hundreds of new stars each year. They are often born from the collisions of massive spirals whose gas has been driven inward, feeding black holes and igniting colossal bursts of starbirth. Infrared galaxies were once rare in the nearby universe, but were common when the cosmos was young, an age of fire and dust. When galaxies grew quickly through frequent mergers, their glow, invisible to human eyes, is captured by infrared telescopes that can pierce the dusty veils hiding their cores. Through them, astronomers glimpse the universe's most fertile epochs, when galaxies were still wild and unfinished, blazing their way into maturity. Even measuring a galaxy's size reveals the subtlety of these vast structures. Unlike planets or stars, galaxies have no clear edges. Their stars thin out gradually, fading into the dark until they merge with the faint glow of intergalactic space. Astronomers use different methods to estimate their boundaries, tracing the brightness of their light, the density of their gas, or the limits of their dark matter halos. But in truth, a galaxy's edge is not a border at all. It is a whisper, the place where gravity's pull fades and the endless night begins again. Galaxies collide, merge, flare, and fade, each one a living system shaped by time, matter, and motion. Their interactions seed new stars, awaken black holes, and sculpt the architecture of the universe. To watch them is to see creation and destruction as one continuous process, gravity's slow heartbeat echoing across billions of years, building the cosmos we call home. Back in 1936, Edwin Hubble, the same astronomer who revealed the expansion of the universe, turned his attention to another challenge, measuring the true size of galaxies. His first method was beautifully simple. By measuring how wide a galaxy appeared in the sky and combining that with an estimate of its distance, he could calculate its angular diameter, or metric size. But this approach had limits, since galaxies fade gradually into the darkness of space. Where, exactly, does one end? A more precise standard later emerged: the isophotal diameter. Instead of relying on apparent size, astronomers measure a galaxy's extent based on its surface brightness, how much light shines across each tiny patch of sky. On an image, lines connecting areas of equal brightness are called isophotes. They trace the glowing contours of a galaxy, like elevation lines on a map. The brightness itself is measured in magnitudes per square arcsecond, a way of saying how bright a star's light would be if spread evenly over that small area. The central regions of a galaxy might glow with about 18 magnitudes per square arcsecond, faint to human eyes, but dazzling on astronomical scales. The D25 standard, now widely used, defines a galaxy's diameter as the region where the brightness falls to 25 magnitudes per square arcsecond in the blue part of the spectrum. Beyond this threshold, the starlight blends into the background glow of the universe. Another measure, and perhaps a more meaningful one, is the half-light radius, denoted ARM, the distance from the center that contains half of the galaxy's total light. Introduced in 1948 by the French astronomer Gérard de Vaucouleurs, it became a cornerstone of galactic studies. Later, researchers such as Robert Fish and José Luis Sersic refined it, linking brightness, size, and mass in elegant mathematical laws that still guide modern astronomy. To measure R precisely, astronomers need to capture nearly all of a galaxy's light, no easy task when its outer edges fade into invisibility. In 2000, David Bershady proposed a practical shortcut: find the radius where the local light flux is 1/5 the average overall brightness, then double it. Others have expanded on this with variations that measure how much light lies within 50%, 70%, or 90% of the total. These values are now common in large catalogs like the Sloan Digital Sky Survey, which maps millions of galaxies. The SDSS also helped popularize the Petrosian method, developed by Vahe Petrosian in 1976. This approach measures how a galaxy's brightness falls with distance from its center, defining a radius that captures most of the light while minimizing interference from background noise. In galaxies whose brightness declines smoothly like exponential disks, this method can recover nearly all their light. For galaxies with concentrated cores, such as ellipticals, it usually captures about 80%. One of the strengths of the Petrosian system is its consistency. Because it depends on ratios of brightness rather than fixed limits, it works at many distances and redshifts, but no method is perfect. Early critics, including teams at the Infrared Processing and Analysis Center, IPAC, noted that Petrosian magnitudes could underestimate brightness by as much as 10% compared to isophotal measurements, especially for galaxies with faint outer halos. Later refinements corrected some of these errors, using Sersic's brightness profile to better model light loss beyond the defined radius. As infrared astronomy matured, new techniques emerged. The 2-micron all-sky survey, 2MASS, extended the study of galaxies into the near-infrared, observing stars invisible to optical telescopes cooler, older, and often hidden by dust. In this survey, astronomers such as Thomas Jarrett defined galaxy sizes using the K-dot band isophote at a brightness of 20 magnitudes per square arcsecond, corresponding to light with a wavelength of 2.2 micrometers. They also used several other measures: circular apertures, total flux distributions, and the Cron aperture, which encompasses roughly 90% of a galaxy's total light, by multiplying the average flux radius by 2.5. But galaxies do not exist as solitary specimens in a cosmic museum. Almost all of them live in groups or clusters, bound together by gravity. True loners galaxies that have escaped interaction for billions of years are rare, perhaps only 5% of all known galaxies. Even these isolated systems often have smaller satellites or faint evidence of long-ago mergers etched in their halos like scars from ancient encounters. On the largest scales, gravity and cosmic expansion are locked in a constant tug of war. Hubble's law tells us that galaxies drift apart as the universe expands. Yet within clusters, gravity holds them tightly enough to resist that pull. These gravitational gatherings likely began early, when invisible dark matter clumped together, drawing gas and galaxies into its wells. Over time, small groups merged into vast clusters, where collisions and infalling gas heated the intergalactic medium to astonishing temperatures tens of millions of degrees Kelvin. In these cosmic cauldrons, the numbers are striking. Around 70–80% of a cluster's mass is dark matter. 10–30% is scorching gas that glows in X-rays. And only a few percent lies in the galaxies themselves. At the heart of many clusters sits a single brightest cluster galaxy, BCG, a giant elliptical grown fat on mergers, surrounded by hundreds or thousands of smaller companions. Clusters, in turn, gather into even greater structures, known as superclusters. Immense webs of galaxies connected by filaments of dark matter and surrounded by vast, empty voids. These filaments thread the cosmos like veins of light across unimaginable distances. The largest known structure, the Hercules Corona Borealis Great Wall, stretches nearly 10 billion light-years, a span so vast it strains our definition of uniformity in the universe. Our Milky Way resides within a modest local group, about 1 megaparsec across, roughly 3 million light-years. Alongside the Andromeda Galaxy and a few dozen dwarfs, it drifts on the outskirts of the Virgo supercluster, itself just one lobe of an even grander formation called Laniakea Hawaiian, for immense heaven. Within this boundless structure, hundreds of thousands of galaxies are linked by gravity into one graceful, sprawling pattern. And within each galaxy, another invisible structure shapes its destiny: magnetic fields. Though faint, these fields thread through the interstellar gas, guiding the flow of charged particles and helping sculpt spiral arms. They influence how gas clouds spin and collapse, channeling angular momentum so that new stars can form. In this quiet, unseen way, magnetism is a hidden architect of galactic life, the subtle force that whispers order into chaos, shaping the luminous spirals we see across the night. From Hubble's careful measurements of faint isophotes to the colossal maps of superclusters stretching across the cosmos, the story of galaxies is one of scale and connection. Each one, no matter how distant, is part of a vast pattern woven together by gravity, dark matter, and magnetic threads into the living fabric of the universe. Magnetic fields thread through the disks of spiral galaxies like invisible rivers of force. On average, they measure about 10 microgauss, roughly a billionth of the Earth's own magnetic strength. In comparison, our planet's field is about 30 microteslas, tens of thousands of times stronger. Yet even this faint cosmic magnetism shapes the rhythm of galactic life. In galaxies like Andromeda, M31, or Triangulum, M33, the fields are gentler, about 5 microgauss. But in star-forming spirals, such as M51, M83, or NGC 6946, where stellar nurseries blaze within their spiral arms, the field can double or triple in intensity. Inside these arms, dense clouds of gas and dust amplify the magnetic lines, pushing them to 25 microgauss. The true extremes occur in starburst galaxies M82, the antennae galaxies, and others, where the chaos of rapid starbirth and supernova explosions drives magnetic strengths up to 50 or even 100 microgauss. Modern cosmology explains the origin of these great galactic engines through the LCDM model lambda cold dark matter. About 300,000 years after the Big Bang, the universe cooled enough for the first atoms of hydrogen and helium to form, a period known as recombination. Light could finally travel freely, but there were still no stars, only dark, neutral gas. This was the universe's dark age, when tiny ripples in matter density began to grow under gravity's pull. Within halos of cold, dark matter, ordinary gas condensed into the first protogalaxies, enormous clouds of hydrogen collapsing toward their centers. As they fell inward, these gases heated up and resisted further collapse until they could cool by radiating energy away, a difficult task in a universe lacking heavy elements. Only hydrogen molecules could emit heat, and they were inefficient at doing so. Over hundreds of millions of years, gravity sculpted these collapsing clouds into rotating disks dense enough to spark the first star formation. The earliest stars, called Population 3, were made almost entirely of hydrogen and helium. They burned fiercely, their ultraviolet light ionizing surrounding gas and carving brilliant bubbles into the darkness. As their light spread, it re-ionized the universe, turning neutral hydrogen back into plasma and brought the Dark Ages to an end. These massive first stars soon died in supernova explosions, seeding the cosmos with the first heavy elements, the raw material for later generations of stars and planets. Their ashes gave birth to Population 2 stars, metal-poor but more stable, which began assembling the young galaxies we see in the early universe. Astronomers now model these early epochs with remarkable precision, comparing theory with data from the James Webb Space Telescope and other observatories. Some early JWST results hinted at galaxies so distant they appeared to exist only a few 100 million years after the Big Bang, at redshifts near 16, but later analyses corrected some to lower values. The process remains difficult. Faint light can mislead, and even the color of a galaxy can mimic greater distance. Detecting individual Population 3 stars is harder still. For a time, a galaxy known as Cosmos Redshift 7 seemed to show spectral evidence of such primordial stars, but later, studies revealed oxygen lines inconsistent with their pure hydrogen-helium makeup. Step by step, however, the evidence grows clearer, and our picture of early galaxy formation becomes sharper. Once stars ignite, galaxy evolution accelerates. Within about 1 billion years, the main architecture of a galaxy takes shape. Clusters of ancient stars form. A supermassive black hole grows at the center, and a central bulge of Population 2 stars emerges. This black hole soon exerts feedback control over its surroundings, limiting how much new gas can fall inward. After a few billion years, the matter settles into a rotating disk, and a more stable galaxy begins its long life. Galaxies continue to evolve by gathering new material from the cosmic web streams of hydrogen, helium, and small dwarf companions. This steady inflow fuels cycles of star birth and death, enriching the interstellar medium with heavier elements and enabling the formation of planets. The rate of star formation depends strongly on environment. Galaxies adrift in vast voids tend to form stars most efficiently, while those crowded inside dense clusters form the fewest, their gas stripped away by the cluster's harsh conditions. Collisions between galaxies also shape their destinies. In the early universe, such mergers were frequent and chaotic, producing galaxies with warped and irregular shapes. While most stars glide unharmed through these encounters, their galaxies' gas and dust are violently stripped, forming spectacular tidal tails, streaming arcs of stars drawn out by gravity. The antennae galaxies and NGC 4676 are famous examples of this cosmic choreography. Even our Milky Way is part of the dance. It is slowly approaching the Andromeda galaxy at about 130 kilometers per second, and in roughly 5 to 6 billion years, the two will merge. Their stars will weave together into a single, enormous elliptical galaxy, and the night sky, if Earth still exists, will blaze with new constellations of colliding starlight. The Milky Way has already swallowed smaller companions in its past. Cosmological simulations suggest that around 11 billion years ago, it merged with a sizable galaxy known as the Kraken, leaving traces still visible in the motions of its oldest stars. Major mergers like this are rare today, but they were common when the universe was young. As time passed, the pace of these grand collisions slowed. The most massive galaxies reached maturity, their shapes largely fixed. Star formation across the cosmos began to decline about 10 billion years ago, marking a quiet turning point in galactic history. Since then, galaxies have aged gracefully, fewer in number, gentler in growth, and bound together by the same cosmic forces that first set them spinning in the dark. The universe, boundless and breathing with light, is filled with stars, and around many of those stars circle their own quiet families of worlds. For most of human history, these planets existed only in imagination. We could look through our telescopes and see the familiar faces of our own system, Mars glowing red, Jupiter banded and immense, but beyond that, the heavens seemed unreachable. The idea of other worlds, each lit by its own sun, was once a dream, whispered by poets and philosophers. That dream began to take shape only in the last few decades. As technology sharpened our senses, we started to glimpse faint signs of exoplanets, worlds orbiting stars far beyond our Sunday. These planets do not shine with their own light. They reveal themselves only by the smallest hints, by how they tug at their stars or dim their glow for a fleeting moment. The first confirmed exoplanets were found in 1992, and they were utterly unexpected, circling not a living star, but a pulsar, the dense spinning remnant of one long dead. These strange pulsar planets proved that worlds could endure even in the aftermath of stellar death. Then in 1995, a planet called 51 Pegasi b was discovered orbiting a sun-like star. It was a giant world, scorching and close to its star, a hot Jupiter. That discovery opened a new era. Finding such planets is a delicate art. Astronomers use several ingenious methods to detect their presence. 1. The radial velocity, or Doppler method, measures the minute wobble of a star as it is pulled by an orbiting planet's gravity. The motion shifts the star's light, stretching it to red as it moves away, squeezing it to blue as it comes closer. From these tiny changes, scientists can infer the planet's mass and orbit. Another technique, the transit method, watches for a planet crossing the face of its star, dimming the starlight by a fraction of a percent. This method has revealed thousands of planets, especially through the Kepler Space Telescope, launched in 2009. Kepler stared for years at a small patch of sky, watching over 150,000 stars for the faint rhythmic blinks of orbiting worlds. What it found transformed our understanding of the cosmos. We learned that planets are not rare, they are the rule. They come in astonishing variety. Immense gas giants like Jupiter, small rocky worlds like Earth and Mars, ice giants of water and methane, and even stranger creations, planets orbiting so close to their stars that their skies are oceans of flame or rogue planets, wandering alone between the stars, cast out of their birth systems to drift forever in darkness. Understanding these alien worlds brings us back to the question of how planets form. Every planet begins in the same kind of nursery, a protoplanetary disk swirling around a newborn star. Within this spinning halo of gas and dust, microscopic grains bump and stick, forming clusters that grow into mountain-sized bodies called planetesimals. Over time, gravity gathers these fragments into protoplanets, the embryos of future worlds. Two main processes guide this cosmic growth. The first, core accretion, describes how solid materials slowly build up, forming rocky planets or the dense cores of gas giants. The second, called disk instability, happens when parts of the disk collapse under their own gravity to form massive planets directly. Both processes may act together, depending on the conditions around the star. Temperature plays a defining role. Close to the star, heat keeps water and other ices from forming, leaving metals and rock as the main ingredients perfect for terrestrial planets. Farther out, cold rains and ices condense, creating heavier cores capable of capturing vast envelopes of hydrogen and helium, becoming gas giants. Yet planets do not always stay where they are born. As they grow, they interact with the surrounding gas and with each other, shifting their orbits in a graceful but chaotic migration. Some spiral inward to scorch beside their stars. Others are flung into eccentric, distant paths. Planetary systems, it turns out, are not static. They evolve, collide, and reshape themselves over millions of years. This study naturally leads to the question that stirs every imagination. Could any of these worlds harbor life? Astronomers search for planets within the habitable zone, that narrow band where temperatures allow liquid water to exist. Water is considered essential for life as we know it, though discoveries of hardy organisms on Earth, thriving in boiling vents, acid lakes, and frozen wastes remind us that life's adaptability might reach far beyond our definitions. Some exoplanets lie within these temperate regions, but they are often light years away. With modern telescopes like the James Webb Space Telescope, JWST, launched in 2021, scientists can now examine the faint starlight filtering through a planet's atmosphere, searching for biosignatures, gases such as oxygen, methane, or specific combinations that might hint at biological processes. One day, such a spectrum might whisper that we are not alone. Many stars host multiple planets, forming intricate miniature systems. Some echo our own, with rocky worlds near the star and giant planets farther out. Others defy all patterns, giant worlds crowding perilously close to their suns or planets, locked together in rhythmic orbital resonances, their paths bound in mathematical harmony. These systems reveal that planet formation is not a single story, but a symphony of possibilities, shaped by gravity, chance, and time. Each discovery reminds us that our solar system is not unique. It is simply one verse in a vast galactic poem of creation. The same laws of physics that shaped Earth also sculpted these distant worlds. Somewhere out there, under another sky, there may be oceans that glitter in alien sunlight, mountains of crystal ice, or storms that rage for centuries. And perhaps, beyond the reach of our instruments, a small blue world orbits its star, waiting for us to notice. When the first planet beyond our solar system was confirmed in 1995, it was a lonely data point, a faint signal from a distant star that changed everything. In less than a generation, that single discovery has blossomed into a cosmic archive of thousands. Each new world has rewritten a small part of our understanding, revealing that the universe is far more inventive than we ever guessed. The planets found so far are astonishing in their variety. There are giants so close to their suns that their skies burn with molten metal, and smaller worlds locked in eternal twilight, their faces frozen toward their stars. Some orbit pulsars, the corpses of once living suns. Others drift untethered in the dark, having been flung from their birthplaces long ago. This diversity has forced astronomers to rethink what a planetary system even is, and what hidden possibilities might exist within the quiet light of every distant star. Studying these worlds also turns our gaze homeward. The more we learn about exoplanets, the more fragile and improbable Earth seems. Its distance from the Sun, its moon that steadies the planet's tilt, its magnetic field that shields life from radiation, its balance of oceans and continents, all are rare harmonies. And yet, by showing us how many different combinations the cosmos can produce, exoplanet research hints that life's conditions might not be as unique as we once believed. Somewhere, under another sun, there may be chemistry quietly beginning to think. Astronomers now probe the atmospheres of distant planets by reading the fingerprints of light in their spectra. They detect traces of water vapor, methane, carbon dioxide, and sodium molecules that tell stories about heat, pressure, and history. Some worlds may hide vast oceans under icy shells. Others may smolder under a greenhouse sky of carbon dioxide. A few may be volcanic worlds with glowing plains of lava where a single day could outlast a human lifetime. These details are more than curiosities. They reveal the physics of how worlds breathe, change, and sometimes die. The lives of planets are tied to their stars. Young suns are fierce and unstable, bathing their planets in storms of radiation that can strip atmospheres bare. Later, as they age and swell into red giants, they can consume their closest companions or scorch those just beyond reach. Even when they fade into white dwarfs, the remnants can still host planetary ghosts, asteroid belts, and shattered fragments tracing silent orbits around the cooling core. Every planet's fate is written in the long story of its parent star. Across the Milky Way, the picture widens. In dense clusters, where stars crowd together, radiation and gravity sculpt planetary systems differently than in the quiet solitude of galactic suburbs. Metal-rich regions tend to birth larger worlds. Metal-poor ones yield small, rocky planets. The story of planets, it turns out, is inseparable from the story of galaxies, their chemical evolution, their bursts of star formation, and the slow enrichment of matter from one generation of stars to the next. Behind every discovery lies extraordinary technology. Precision spectrographs can detect the tiniest tremor in a star's light. Adaptive optics sharpen ground-based telescopes to see through the turbulence of Earth's air. Space missions like Kepler and TESS have scanned millions of stars, searching for the faint shadows of transiting planets. New observatories, JWST, and soon Plato and LUVOIR, promise to study even the faintest atmospheres, teasing out clues of clouds, chemistry, and perhaps the signatures of life. Yet despite all we know, mystery remains the rule. Why are hot Jupiters so common when our own system has none? Why do some planetary systems form in perfect symmetry while others are wild and chaotic? What hidden processes decide whether a planet grows into a rocky Earth, a gaseous giant, or a frozen wanderer? Every answer uncovers deeper questions. The science of exoplanets is young, and the cosmos still holds its secrets close. What drives it all is curiosity, the same impulse that once led early astronomers to aim their telescopes toward the night sky and wonder what those faint lights might hide. Each new exoplanet discovered is a small revelation, a glimpse into another solar system, another experiment in creation. These worlds remind us that the universe is not static, but restless, forever building, breaking, and beginning again. From the first pulsar planets of 1,992 to the thousands catalogued today, exoplanetary science has become one of humanity's grandest adventures, a conversation between observation and imagination. It is not only about finding new planets, but about understanding our own, how it formed, why it endures, and how fragile its balance truly is. As our instruments grow sharper and our reach extends farther, we may one day find the unmistakable signs of life, perhaps not like ours, perhaps stranger, or perhaps we will find silence, the vast quiet of worlds without witnesses. Either way, the search is its own reward. Each discovery, no matter how small, reminds us of the beauty of not knowing, of asking, and of daring to look outward into the deep. And now, as the echoes of distant worlds fade into the quiet, let yourself drift with them. The stars you've traveled through tonight begin to dim, their light softening like embers at the edge of sleep. Somewhere out there, planets still turn in their long, slow orbits, and the universe hums its endless lullaby of motion and silence. You don't need to reach for it anymore, just breathe and let it all move around you. The rhythm of your own heartbeat joins the pulse of the cosmos, steady and calm. Thoughts dissolve like starlight in morning mist. The galaxies recede, the sky grows deeper, and the only sound that remains is the gentle hush of your breath. Rest now, traveler among the stars. The night is wide, the universe endless, and sleep is its quiet mirror.